Okay, sorry for that. So I'm going to talk about dipolar relaxations and molecular crowding, how we can take advantage of the dipolar relaxation to address the molecular crowding on in vivo model. This is a collaboration with many people, Irene Vorontsova, Alex Valmichana, Belén Torrado, and the group of Tom Schilling, Jim Hall, and also Enrico. And basically what we want to understand here is, how basically the organization of the lens in zebrafish take place and how is important the molecular crowding in order to have a functional lens that enable you to see or not. And basically the group was working on aquaporin zero, which is important for the homeostasis on the water in the lens. And basically, we will use all the techniques that we talked today, in particularly the Agdan, which is, I will cover in a minute, a small brother of Lardan, and basically the spectral phasor for achieving that. So the inspiration or the motivation of this came for my early work. We already went to this today morning, the organization of these lamellar bodies, which in other words are molecular crowding at the level of this organelle. And then when I moved to the LFD, I was interested in using another probe, Lardan, to understand the dynamics of the chromatin inside the nucleus. And basically, we did a lot of work with this probe, understanding the dynamics of water within the cell in vivo. And when I was doing this, I met Irene Vorontsova, and she was interested in water in the lens. And basically, we put things together, and we say, well, maybe we can do a collaboration on that. So the particularity of Agdan, I'm not going to the photophysics, but the particular of Agdan is that Agdan has as a substitute in this R group, basically a methyl group, which basically reduce and the hydrophobicity, enabling Agdan to move around in the cell and losing completely affinity for membrane. It can be at the interface of membrane, but it's diffusing everywhere. And we demonstrate that it's also inside the nucleus, and you can see the dynamics of water in the chromatin, AU, enterochromatin, and everything. And it's a really valuable approach that many other people have used before, like Luis Bagatoli, to understand the dynamics of water in cells and organelles. So the thing about the lens is, well, the lens is a very special organ in the eye because it has a transverse condition, and the correct optics is needed in order to focus the light in basically the retina to be able to see. If we have any distortion in the lens developed, it will basically produce a point, a focus point after or before, and it will produce damage of the vision. The thing is that to study the evolution of the lens, Irene was working with zebrafish because it's a great model for imaging. So the fish is transparent. It has a rapid development. It's very small, so we can easily fit on top of inside a dish and on top of a microscope. As I say before, it's transparent. And also it's important the point that you can even manipulate genetically in order to do, more complicated studies. Irene was particularly interested in understanding how the aquaporin zero was relevant for, the development of the eye, and in particularly, aquaporin zero is necessary for the lens transparency. So if there are any mutation, deletion of aquaporin zero or A on B. I didn't say, but it's important to say that this duplication is due to the duplication in the teleost fishes, and the two has different properties, and this was part of the previous work of Irene, in which she shows that the aquaporin 0 has a very strong phenotype. The aquaporin B knockout is not that bad, but when you have the double mutant, you have really a strong phenotype, and this is a blind fish due to cataract. So to address our problem, what we wanted to do is basically, well, stain our fish with Agdan overnight, and then we put in our dish the fish facing with the eyes to the bottom, and then we image using hyperspectral imaging and multiphoton excitation in order to get through the whole lens. And then we calculate our spectral phasor for the images, and we did a wonderful analysis in combining basically the spectral imaging with phasor and traditional imaging processing. And this was a responsibility of Alex Bagnisciana, that you met him early in the morning. He did really a wonderful coding in order to address the dipolar relaxation at different points in the radial distribution, so we can define the center and then the perimeter, and then we will have the profile of dipolar relaxation for all the angles around the lens. And using this approach, we can quantify the distribution of water and molecular crowding on the lens. So the first test that we wanted to do was to, well, okay, check how the Agdan is able to respond to molecular crowding. And the most important protein in the lens is the crystalline. Crystalline can reach really high level of concentration, above of, we reach here something like 350 milligram per milliliter, but in in vivo, you can go even higher, which is really a shell. It's not more a solution. And when we put basically Agdan in increasing concentration of crystalline, you can see that it shifts towards shorter wavelength. So it's getting bluer, which means that the relaxation is decreasing. And you can see here how it's calibrate our system. And we define a change in dipolar relaxation as a change in the phase, as I saw in the plot. So then we have fishes that we image at different stages. And I have to say that the day 5, as far as I learned, is when the lens became mature and the fish is able to see. From the early stage to the day 4 or 5, the lens has still in the cell organelles, but after these, the organelles are gone, and the organization and homeostasis depend basically on the osmotic pressure to bring the nutrient and remove the waste. So these are the images, and a point that I want to stress is if we go back, if you go back here, you see that the intensity image is not much. There is not much information. There is only a strong intensity in the center, but you cannot see much in the intensity. But when we transformate the image and color the image with the dipolar relaxation scale, which is here, we can see a strong change in the dipolar relaxation along the development, right? And we can quantify this due to the analysis that Alex did. And basically, we can see that as the lens develop, to measure the lens develop, we measure the diameter of the lens done. And this is the normalization of the radial distribution. And we can see that from the day 2 to the day 9, the higher dipolar relaxation shift from the center of the lens to some point in the equatorial plane, right, of the lens. The lens is divided by the core in the center, and then we have equatorial, and then we have the epithelium in the perimeter. And we can also, do the calculation for more than 60 and 90 lenses, and we can see that this is sort of a sigmoidal trend that we can quantify and propose what is going on here. By segmentation, we can also see that there is a correlation between growing, right, and decreasing in the dipolar relaxation and the core, right, of the lens. And this is important because this decrease in the dipolar relaxation means that the lens is maturating and is reaching the index of refraction need in order to focus the light at the retina as it needs for the proper vision. We did also analysis of the anterior and posterior plane because the closing of the lens is very important in order to have a good physiology. And what we learned is that in the anterior plane, the correlation also goes from higher dipolar relaxation to lower dipolar relaxation. And in the posterior plane, it has a different behavior that it's increased at the day 5 and then close. And this is also everything related to the suture, which is where the cells are getting close and tight in order to, organize the influx and efflux of water and the waste on the animal. So due to the 3D, analysis that we can do, by the CT stack with the multiphoton, we wanted to answer if the distribution of dipolar relaxation was conical or was parallel, because there was a question that we want to address is if this is a core or is a tube, right, in the lens. The lens is not round; it has like a more round in the top, and then it's a cone in the bottom, right? And basically by segmenting at the different height and then measuring the distribution on parallel or in a cone, what we discover is that, well, the distribution of water was spherical, and this was something important to also learn in the model. But finally, what we wanted to do is, well, to understand what happened with the aquaporin and how aquaporin influenced the molecular crowding inside the lens. And these are results from previous work of Irene, and we can see that the transparency is changed when you have the double mutant as well as the single mutants. But what happened with the dipolar relaxation? Well, what we learn is that dipolar relaxation changed very importantly in the two situations, so the single mutant, but more significant when we have the double mutant. The most important thing to highlight here is that when we go from the wild type, this I didn't say, but this is an animal in a mature situation of the lens, so this is day 5. So if we compare this to this, you see that the dipolar relaxation is increased, and this basically modify the index of refraction inside the lens and avoid the lens to proper work and be able to see. And the aquaporin B does not affect at the core. It increases a little bit the dipolar relaxation in the equatorial plane, but more or less is similar to the wild type. And when we watch at the aquaporin 0, double mutant aquaporin 0, you can see that there is a dramatical effect on the equatorial plane that really avoid the proper vision. Considering the imaging processing analysis that we have, well, we measure the average distribution, dipolar relaxation for all the angles on the lens, and then we did calculation, and what we discovered is that the major effect are in the inner and outer cortex of the lens, and we can quantify this and propose what was happening. We did the same for the we show for the development in the anterior and posterior plane. And what we discover is that the dipolar relaxation is lower in a region in the aquaporin A0 negative, so the knockout. And there is a clear disruption between water and transport because we have information from previous work that, aquaporin 0 relies on water transport activity, and while aquaporin B has activity on water transport, it also has compromise in the adhesion between the cells. So finally, well, we quantify this and we show that, in the core, you see in the cortex, you have this, decrease in dipolar relaxation in the aquaporin 0. Is it corrected in disorder? There is not much change in the cortex, but there is a strong change in the suture in the front between the aquaporin 0A versus the other two mutant. So to conclude, basically what I want to say is that the ACDAN provides a ruler to monitor the dipolar relaxation, and therefore basically is a ruler to study the water dynamics on in vivo animals. And basically what we learn is something that is important because, well, molecular crowding and water homeostasis is crucial for lens, otherwise you cannot see. And the dipolar relaxation is high basically, and is connecting with the swelling of the lens. And what for me impressed me the most is that while we connect a molecular process, which is molecular crowding, with an organ physiology effect, because if you affect molecular crowding, the fish is not able to see. So it's really something that, you most of the time listen about molecular crowding roles in cell physiology, whatever, but this is an organ, no? It's an animal that cannot see because of molecular crowding affectation. And then we tackle an important thing related to the role of aquaporin 0A or B, because something that was in the discussion was the role in the water homeostasis, so water diffusion across the different part of the lens, and the adhesion part by the aquaporin B, 0B, sorry. So just to finish, I want to say that something that is more in the perspective, but I think is very interesting, is I talked today about the idea of using sine cosine combined with the light sheet. And in this paper, we tested something which is important because, well, we stain animals with Laurdan, but now we acquire really set a stack on the time that we can acquire a plane in the confocal microscope. So this really open up the possibility to study, processes in our gentle illumination, but also in dynamics on animals, which is a fantastic thing. So the only thing that I miss to say is that, well, this work is now under revision, but is available now in bioRxiv. So I hope we have our finger crossed that can be accepted soon. And with this, I want to thank all of you for your attention. And of course, the team, Irene, Alex, Belen, for all the work. And also the boss, Jim, Tom, and Enrico, that enable us to do this collaboration between the four of us. So thank you very much. And I'll be happy to take questions.